let's consider elastic potential energy and the energy stored in a spring, okay, and gravitational potential energy and the energy stored due to gravity, and kinetic energy, the energy an object has due to its motion, right? I'm going to have three pictures. Let's say I have a ball, starts up here. I drop it, it hits this spring, okay? The spring is initially right here. Okay, right here this thing has got a whole bunch of gravitational potential energy. It's mgh, right? Now, split second later it falls, it hits the spring, but it's just now getting to the spring, so the spring hasn't compressed. So right here, that's as fast as the ball is ever going to move. And now all its energy is kinetic energy. That's 1/2 mv squared. Okay, now ball hits the spring compresses. Okay, and so now the spring is down here, and this is as low as the ball ever gets. And now I've got the elastic potential energy, okay, 1/2 kx squared, where x is the distance that this thing compressed, x. Now the issue is, I said this spot right here was all kinetic energy. And the reason I can say that is because I said the ball's hit the spring, it's at its lowest point. So I called this my zero gravitational potential energy. But now I'm down below my zero gravitational potential energy, which means I have a height again. It's a negative height, but it is a height. So I actually have to deal with that. Okay, over here I'm going to have to deal with that energy. And so I'm going to add on the gravitational potential energy, which is m times g, but now I have this, and this is a negative height because it's below where I started, so negative x. Okay, and now I've got the law of conservation of energy. Now I can deal with this. So let's say that that ball has a mass of 2.6 kilograms. Let's say it starts an initial height of 55 centimeters up. And let's say it compresses the spring, that x is 15 centimeters. Okay, I want to know the spring constant. Find me k. Alright, so we start at the beginning. The total energy at the beginning, since I'm measuring from right here, is mgh, which is 2.6 times 9.8 times 0.55. That's the total potential energy in the spring. Now, I'm going to skip this part because the ball hasn't stopped here. It's still in motion, so I'm going to go right down to the end. This is what I really am interested in. Elastic potential energy in the spring. So this is equal to 1/2 k, which is what I'm looking for, times x, which is 0.15 squared, plus m, 2.6, times g, 9.8, times h, except h is negative x, negative 0.15. Okay, so now I have 2.6 times 9.8 times 0.55, and I'm going to go ahead and add this term over because it's negative. Okay, so plus 2.6 times 9.8 times 0.15. Now think about this. I'm basically telling you that this initial position up here has got to add on this 15 centimeters of compression. So I've basically just increased my initial height from 0.55 to 0.7 meters, and this is now equal to 1/2 kx, which is 0.15 squared. Okay, and so this makes perfect sense if you think about it. We're saying, well, we should have put our zero down here. But sometimes you don't know this distance, so you can put zero wherever you want, but you got to keep track of all your heights. Okay? If you finish working out the math here, you're going to end up with 2.6 times 9.8 times 0.7 divided by 0.15 squared, and then this whole thing would be multiplied by 2 because of that half, and that equals k, and so k is about 1,590 newtons per meter.